Okay. Welcome, welcome. Two. Okay. Um, all right. Let's have a little fun today. No calculations, unless you find that fun. I do sometimes. We're just going to talk about stickiness today. Okay, that's going to be a theme of lab next week. Okay, last lab of the semester. Oh, not next week. Hey, turkey next week. Let's go.
Yeah, Friday.
Let's go. I need some turkey badly. All right. All right. So today we're talking about stickiness. Okay. Maybe it's spelled that way. I don't know. With a Y. All right. The fancy term for stickiness, chemical term, is intermolecular interactions. But I don't want you to overthink the concept we're talking about. And we're just talking about stickiness. What makes stuff stick to stuff? Okay. What makes adhesives work? Or even getting more simple than that, what makes water water? Why does water stick to itself? Why is it a liquid? Why is it not a gas? Okay. That is the theme of today. So we'll be like drawing different like atoms and molecules and stuff, and we're gonna figure out like what makes it stick to itself. You know, why is methane a gas? Ammonia is also a gas, but compresses into a liquid way more easily. And then you have water, which is a liquid. Okay, so little things like that, right? All right. So I think a good way of warming up this subject would be to talk about solids, liquids, or gases. Okay? And we're going to try to determine what force is the most dominant between solids, liquids, and gases. Okay, so let's make a little table. And we're going to compare two categories. Okay. Intermolecular interactions, also known as intermolecular forces. IMF, or II for intermolecular interactions. Ooh, the heat's turning on. Let's go. Whew. All right, and then the other side, we're going to call it kinetic energy. KE. All right. And if my informal way of referring to intermolecular forces is stickiness, my informal way of referring to kinetic energy is bounciness. Okay. Craziness. Okay. Things moving around. Okay. So we got stickiness versus bounciness. Make up some words today. So without any high-level mathematics, I think we can do this analysis. All right. So intermolecular forces bring things together. Kinetic energy, which of course increases with heat, breaks things apart. Okay, together versus apart. Okay. And kinetic energy is equal to half of mass times the velocity squared of a particle. No, that's not going to appear in a quiz. That's just some background physics. So if you bump up the temperature, you're bumping up the velocity, making things move more. Higher temperature meaning more velocity, therefore more kinetic energy. All right, so if you're a gas, what's winning? We can only choose one check mark. Who's the winner? Yep, bam. Okay. Because in gases, all your particles are far apart. Okay, they ain't sticking to each other. Okay. And then for liquids and solids, well, they are together. So it kind of goes like that. I put the liquid check mark still in the IMF box, but I put it closer to the edge to kind of show you that, hey, it's closer to being a gas compared to a solid. Okay. You've put in some kinetic energy. So to make intermolecular forces lose, one easy way is just heat up stuff. Okay. You heat up stuff, then I don't care how strong your intermolecular forces are, your kinetic energy will win out. Okay. That's what you do with water. Okay. It takes forever for water to boil, right? But eventually you'll get it to boil. Pump in enough heat in there, you'll get it to boil. Okay. And those strong hydrogen bonds, and we'll be talking about hydrogen bonds a lot today, will break apart. Okay. So this is kind of how it goes. Okay, so in summary, for solids and liquids, we can say that intermolecular interactions are stronger than a kinetic energy. And for gases, we're just going to write that inequality the other way around. Okay. Okay. Gases was the subject of last week's lab. I will put an optional extra credit homework on gases over the break. If people want to get a little extra credit, learn some stuff. I'm not going to mandate it. All right. So, pause for your questions here. The remaining focus of today is to talk about the 3 different types of intermolecular interactions more specifically. Okay. All right. Cool. All right. First, we're going to have a spectrum of interaction strength. I guess this left arrow should actually have a stopping point because it's 0. Nothing. Okay. We're going to go from none to strongest. All right, the first thing we're going to do is write down some abbreviations. We're going to write down LDF here. I'll tell you what that means in a moment. Then we're going to write D-D. And we're going to write H bonds. Okay. All right. Now, I'm going to assign color to each of these categories. You don't have to do that if you don't have colored pens, but what I'm going to try to show is there is some overlap in these rankings. But basically, this will be the gist of our rankings today. Whatever LDF is, it's going to be the weakest. DD will be the middle list to make up a word. And then H bonds will be the strongest of everything we've written so far. But there are exceptions to that. We'll explore that like a tiny bit, but meh. Okay. And then I'm going to put a dividing line right about here. Right about here. And everything to the left of the dividing line, we're going to call intermolecular. Here's what I show. This is what I mean by intermolecular. If we draw a water molecule like this, this is H2O number 1. Okay, this is an H2O molecule. If we were to have this water molecule stick to another water molecule, we could draw that interaction. Okay. Here's our H2O number 2. Got 2 lone pairs on that oxygen. All right. And kind of how we like drew a little bit of interactions between acids and bases last class, this is kind of a similar thing. All right, you have this oxygen pointing at the hydrogen. Okay. Yellow's not showing up. I'll go with the color purple. Okay. And this would be an intermolecular interaction, or IMF. I can't decide on my abbreviation now. Maybe IIC, intermolecular interaction. Okay. So inter meaning happening between molecules. Intermolecular. Whereas everything to the right of this dotted line, we're going to call it intramolecular, which means within the molecule. Okay. So everything to the left is known as intermolecular interactions, intermolecular forces, also just known as weak forces. Whereas to the right of the dotted line, anything that's happening within a molecule, that means you're talking about how an atom is interacting with another atom. We already have an existing word for that. They're called bonds. It's your business as usual bonds. Okay. Interactions within a molecule is a bond. So everything to the left of the dotted line, we don't call them bonds. Well, maybe hydrogen bonds. We call them a bonds, even though often they're not technically considered to be bonds. Okay. All right. And how do we rank a different type of bonds? Okay, we have covalent bonds. And then we have ionic bonds. Okay. Ionics, generally speaking, are stronger than covalent bonds. Okay. You can put in metallic bonds in there as well. But there's definitely plenty of exceptions to that. All right, this is not going to be a review of bonds today. We did that like 2-3 months ago, and that's not the focus today. Today is going to be on this weak side. Okay. We're not making molecules today. We're just considering how they stick onto each other. Okay. The field of study that pays close attention to the weak forces is called supramolecular chemistry. Okay, which is, say, beyond, supra meaning beyond. Okay, you're looking beyond just a molecule. Okay, you're looking at what's around it, not what's in it. Okay, right. Supramolecular chemistry made the news a few days ago. They assembled, they use these concepts to assemble this crystal called a MOF, metal organic framework. Okay, and it is this cage structure. Okay, think of it as like this hollow material with huge cavity sizes. Okay. Did I draw this right? Yeah, right there. All right. Anyways, you have these cages, and because they're really hollow, they have enormous amount of surface area. Like the analogy they gave was like 1 tablespoon of this very hollow material has the same amount of surface area as 6 football fields. Okay, 6 football fields worth of contact area all in a tablespoon of this crystal stuff. Okay, and they're trying to use it for like absorbing, carbon dioxide or whatever to, reduce emissions and whatever. Right. And another aspect of these materials they're looking for is, can we absorb hydrogen gas with all this surface area so that we can have like solid state hydrogen based batteries, more power, cleaner power, stuff like that. All right. My chemical background is I was making similar materials, but uranium based. The popular, most robust MOFs are zinc based typically, and they have these zinc nodes. Okay. Cool, interesting stuff. Okay. All right. And there's some vocabulary, and now we're going to go into each of these very specifically, and that might take the whole day or whole class. Okay. Alrighty. Oh, still writing, or are we good?
No.
Okay, swell. All right. All right, let's start. Let's start with, I can't say one's more important than the other. We'll just go in order from weak to strong. All right, so we're going to start with LDF, okay, which stands for London Dispersion Forces. For some people, just say London Forces. All right, forget the first name of the scientist, but I think he was British, but his last name was London. I don't know if he worked in London, but his last name was. All right, London Dispersion Forces. The key point you got to know for London Dispersion Forces is that they exist in all matter. Okay. Even single atoms. Yes, today we're going to explore the stickiness of a single atom. Yep. explore the stickiness of a small atom. All right. And before we get into the details, here's going to be the long story short that you need to walk away with class with, okay? If you have higher atomic numbers, that's going to mean more London dispersion force. Okay. All right, more atoms, more London dispersion forces, and if they have more protons, okay, going deeper in the periodic table, you're going to have more of whatever this London dispersion force is. Okay, and that's because if you have higher atomic numbers, you're going to have more protons and you're going to have more electrons. And folks, this means more charges. You're going to be able to have more charges, and with more charges, there's more stickiness, more potential for plus and minus to stick onto each other and interact. Okay. All right. So higher atomic numbers, more charges. And you may be wondering, but if it's a single atom, how are you going to separate charges? Oh, we'll have an answer to that. We'll have an answer. It's going to be weird. Okay. Let's take a quick look at the periodic table. I think the one on the side will be fine. But for those on the internet, I'll just put out this one. All right, take a look at the periodic table, okay? There are two instances that I want you to be aware of and then kind of throw it away. Let me show you what I mean, okay? I want you to notice that as we go deeper in the periodic table, you've likely noticed this already. I want you to notice that the atomic weights, the atomic masses go up as the atomic numbers go up, okay? And yeah, you know, by the time we get to calcium, it's like 20 and 40, you know, But there's going to be two instances where this isn't true, okay? Look at cobalt and nickel. We go 58.9 versus 58.7. Okay? And then we got tellurium to iodine, 127 to 126. Okay? Now, don't be scared though. That's only two instances where the mass goes down for the average atomic mass. For the rest of the periodic table, you don't have to worry about it because the mass goes up. So what am I saying? What I'm saying is this. It can be very time consuming to look at an atom or look at a molecule, look at some, you know, compound, be like, oh, I got to count up all the atomic numbers. Okay. We can have this very quick and easy approximation. Higher atomic numbers is basically equal to a higher molar mass. Okay. Other than those two elements. But even for those two elements, it was basically equal anyways. Okay. So here's our shortcut, okay, that we'll leave class with. More molar mass is going to mean more London dispersion forces. Okay. And with this shortcut, we can just say, oh, heavier molecule means it's going to be stickier. Okay. That makes life very convenient. Easy case in point, if you were to compare the halogens, which have many similar properties because they are all in the same group. Okay. Fluorine is a gas. Okay. Its molar mass is what, 19 times 2, so about 38 grams per mole about. Chlorine is going to be about 71 grams per mole. Still a gas, but it condenses more easily. Okay. Bromine is around 160 grams per mole. Okay. It's liquid. Okay. Iodine's around 250, 240, 250, somewhere around there. Okay, I'm being very approximate here. It's a solid, y'all. Iodine's a solid. Oh, I should have brought some in here. Darn it. Okay. Oh well. It looks like gray crystals, but in the capsule, you'll see like a purple haze above it because it sublimes. It's one of the few substances that sublimes, which is to say goes straight from solid to gas. Carbon dioxide is another thing that sublimes, dry ice. Solid to gas, straight. Okay. But you can tell that with increasing weight, we have more intermolecular forces, more stickiness. Okay. Liquids have some stickiness, but when your intermolecular forces are so strong, not only are things sticking, but they're rigid. Those interactions are locked in place and specific rather than just kind of bouncing all over the place. Okay. All right, so that's the shortcut. That's the long story short. Let me now get into the long story long of what's going on behind the scenes. What we're going to do is we're going to start out with helium. Okay, let's start out with helium. Okay, helium is the smallest element that can be easily isolated as just the element. Okay. Just, yeah. That's what I'm talking about. All right, helium, it's a noble gas. Okay. You think there's no chemistry here, no chemistry. Check this out. If you think about what a helium atom is, you have 2 protons in the middle, and you have 2 electrons on the outside, sitting in its 1s orbital. Okay. The way I'm drawing helium right now, bless you, okay, I want you to convince yourself that the average position of all the charge is exactly in the center of the nucleus. Let me explain what I mean. The center of positive charge, well, it is the nucleus, okay? Well, what about the electrons, okay? You could say the top is more negative than the bottom. Oh, wait, no, you can't, because the bottom has the same amount negative. Left and right, there's no negative. So the average position of the electrons is also the nucleus, even though it may not actually be in the nucleus at that moment, okay? The average is the center. So this is a neutral helium. I mean, all the heliums we'll be drawing here will be neutral overall, but I mean like as neutral as you can get. Everything is centered. I can write that. Charges centered on nucleus. Okay. So where does this get interesting? We don't see at the moment any potential for helium to stick to itself, but there is scientific evidence that you can make helium stick to itself, and it's darn important, okay? You can buy liquid helium. It can be made. It costs a lot of energy to do it, but it's very medicinally important as well as scientifically important, right? When you're running nuclear magnetic resonance, NMR, what do they call it? MRI. When you run MRI in a medical setting, magnetic resonance imaging, in order for your electromagnet to perform well, to be at superconducting temperatures, you need to keep things cold, all right? And you need liquid helium. Why is liquid helium so darn capable of being cold? Why is it the best choice for being cold? It's because it refuses to be a liquid until, this blows my mind, 2 Kelvin, okay? 2 Kelvin. So at 2 Kelvin, you go from gaseous helium, that's not grams, gas helium to liquid helium at 2 Kelvin. Okay, Just to say it exactly, that is only 2 degrees above absolute zero. You cannot get colder than 0 Kelvin. It is literally and mathematically the lowest temperature. Basically, you almost have to get to absolute zero. But you get to that temperature, okay? You may pre-cool with some liquid nitrogen to help things out so your systems don't have to work so hard. You pre-cool with liquid nitrogen, you use healthier coolers, okay? All these stuff, and you condense to 2 kelvins. And then you know, oh, I got a liquid. But how the heck is the helium sticking to itself, right? It turns out that thermal motion, that is to say the movement due to temperature, exists even down at the atomic level, not just the molecular level. So at any given point in time, you could have an instance where this is an exaggerated picture, but it'll help. You could have an instance where your electrons are more on one side of the atom than the other. Okay. That's due to thermal motion, just a natural temperature bounciness of stuff. All right. And this is called an instantaneous dipole. Instant dipole. Basically, just through the bounciness of life, it essentially happened at random. Yeah. So you got one side that's going to carry a positive charge, but it's not a complete positive charge because those electrons, they're only slightly off, okay? So instead of saying like a full +1 or a full +2, it might be like a 0.5 or a 0.1. Okay, in reality, for something as small as helium, it's like the equivalent of like 1/100th of a proton or something. All right, so it's really dinky, but it is there. And so we're going to introduce a new symbol, the lowercase Greek letter delta, okay, which kind of looks like some music note kind of thingy. Okay, and that stands for partial. Okay, it's a partial positive. Okay. And the other side where the electrons are at, you have a partial negative. And what if this had happened nearby for another helium atom? You have a positive side, you have a negative side. And just like magnets, when it comes to charges, in order to get things to stick, they will all be facing the same direction. Okay? So you got minus and plus pointing at each other. And yes, even down to a single stinking atom, you can have an attraction. That is called London Dispersion Force. London force. Yes.
So is it just a coincidence, or is it very similar to what, like how water is, like the atoms are shaped like that? And in my
I think you're slightly onto something. Yeah.
I'm just saying, like,
yeah,
shape.
the short answer is yes, because when water sticks to each other, you have a positive side, you have a negative side, you have something like kind of jutting out, right? You're correct. Yeah. You're gonna see this over and over again. We're gonna have polar molecules. We're gonna have hydrogen bonds, a special case of polar molecules, and you're just gonna see positive, negative side. Okay. And basically, if you don't have like sidedness to your molecule, it's not going to be as sticky. Okay. All right, there's your London dispersion force. All right. And then if we were to compare this to like neon, neon, you'd have like, 10 protons, and then you have like 10 electrons. Okay. If you like electron, 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 electron. Okay. Again, it's an exaggeration, but you can see between two neon molecules, atoms, you have a potential for greater charge separation. Again, this is greatly an exaggeration. In reality, it's like barely off the center. But whereas neon, or excuse me, helium condenses around 2K, okay, neon, big upgrade, not really, but 20 Kelvin, that's still stinking cold, okay? But it's 10 times a higher number, I guess. So these are measurable. These are measurable, okay? All right. Okay. These dipoles can happen instantly or they can be induced. Okay, let me show an induction. I'll go back to helium. If this happened instantly and you had a neutral, okay, here's an instant, and here's a neutral. You're going to have a negative side and a positive side, right? If you have a neutral helium nearby, think about it. This nucleus will have incentive to approach a negative, and your two electrons will be pushed away by the negative there, okay? And then you'll end up with the same picture, okay? So instant dipoles or induced dipoles. Okay. Is our conclusion for London dispersion force. That's how you get things to stick. All right. Before we move on to dipole-dipole interactions, I guess I have to define exactly what a dipole is. I'm only 50% sure I've done that before. So what is a dipole? Dipole is charge separation. Okay. Just like the idea is for many poles in life, you have two equal but opposite ends, North Pole, South Pole, equal but opposite in terms of like geography, right? In terms of magnets, well, you also have a North Pole and South Pole, equal but opposite physics. Okay. And so a dipole, a pole based off of a charge, you have a positive end and you have a negative end. And that's all we mean by a dipole. You have charge separation. Okay. All right, and charges are electric fields, and those can be measured. For those who go on to physics, that's measured in debye, D-E-B-Y-E-S. For Chem 101, you do not need that word ever. Okay. All right, so what are the takeaways? Okay, the takeaways that will help you with any of these sorts of problems. Okay. Gotta put this back. Number one, London dispersion forces exist in all matter. Number two, more molar mass equals more London dispersion force. Okay, that's our second check mark. And then number three, okay, know this, they are weak. They're quite weak because the instant dipoles and instant induced dipoles are small and temporary. Okay, they're small and they're temporary. Once one thing we know about life is temporary things tend to be weaker. Okay. Now it's time to. All right. It's weaker because, well, it's not there. Okay. It goes away. And if you're not there, then you can't do anything. Okay. The remaining two categories today of DD, dipole-dipole interactions, and hydrogen bonds will be different because they will all have permanent dipoles. Okay. All right. And in fact, the dipole-dipole interactions and the hydrogen bonds, they are significantly stronger than London dispersion forces. Sometimes you'll see that even lighter molecules, sometimes much lighter than some of the heavier ones with only London dispersion forces. It's like, if you're a lighter molecule, but you have DD and or H bonds, like you're in a new league in terms of how sticky you are. All right, we'll see that in lab next week. Okay, we're gonna see like, you know, we're gonna have a bunch of molecules that you'll analyze that only have London dispersion forces. But then you'll have one that has like hydrogen bonding ability. It's gonna be the like the lightest of all of them, or one of the lighter ones. And its melting point is gonna be like, okay, because it can do H bonds. All right. Pausing for questions, clarifications. All right. Next up, we got DD. Always reminds me of Dexter's Laboratory, little cartoon I grew up with. DD stands for dipole-dipole interactions or forces. Dipole-dipole forces. Okay. And really, it should be PD, because all interactions are dipoles, whether you're a little London dispersion force or you're a covalent or ionic bond, all stickiness is dipoles, okay? It should really be permanent dipole, permanent dipole. Well, that's a mouthful. All right. So you got permanent dipoles. And the only way a molecule will have a permanent dipole is if it's what's called a polar molecule. Okay. And there's some joke about polar molecules involving polar bears, but I forget how it goes, so I'm not even going to try. Okay. A polar molecule, permanent dipole, a molecule with a permanent dipole, it means the same thing. They're synonymous. Okay. So polar molecule has permanent charge separation. Permanent charge separation. That's fancy speak for saying it's going to have a negative side and a positive side. Okay. We're going to have something called a nonpolar molecule. Nonpolar molecules cannot do dipole-dipole. Okay. Or said another way, when it comes to nonpolar, let's compare polar and nonpolar. Let's just compare right now. So everything does London dispersion forces, even polar molecules. But polar molecules will also have DD going for it. Whereas nonpolar will be LDF only, it will have no dipole-dipole. Okay. The most common error for next week's lab is for the polar molecule, people will put an X next to dispersion forces. London forces, whatever, but everything has it. Okay, everything has London dispersion. If you exist, you have London dispersion forces. That's simple. Okay. All right. So we're going to have to figure out what makes a molecule polar, what gives it charge separation. This is a difficult concept sometimes for students. Okay, so what I'm going to try to do is give you 3 or 4 different ways of thinking about it. Okay, so how are you polar? To be a polar molecule, polar molecules, and we could define this several ways. All right, so we talked about the permanent charge separation. I'll just rewrite that point. Okay. And we can apply some mathematical tests. Okay, the first one I'm going to call a coordinate test. Okay. And in terms of coordinates, if you assign the coordinate 0, 0, 0, the origin of a 3D graphing system to your central atom, okay. If 0, 0, 0 is the location of your central atom, 0, 0, 0 will not be equal to your center of positive charge or negative charge. It will not be on the origin. It will not be in the middle. Okay. All right, that is that's the most strictly mathematically rigorous way of saying it. Okay. There is an equivalent way of saying this without coordinates. Okay. It's another mathematical concept called symmetry. Okay. Do a symmetry test. Okay. Now this one's going to sound, I suspect, really terrible for some people, but for others, it'll be like, oh yeah, I got it. Okay. So the symmetry test is this. The axis of symmetrical rotation is not perpendicular to a plane of symmetry. Okay. For the few that are interested in chemistry or physics, careers, this is the most rigorous sort of test applied from a theoretical standpoint. And I'll show this in action. Okay, this does not make great sense in words, but once I show it on like a water molecule, you might be able to see it. Okay. All right. I got one more technical definition out of the way, and then I'm gonna give the easy shortcut. Okay, that works basically every time in one-on-one. Okay. The easy shortcut will apply these tests correctly like 99% of the time for what we do in chemistry, basically 100. Okay. All right, there's one more way you can test. Instead of theoretically, you can do this experimentally. Okay, and this is a physics-based test. You can do the electric field test. Okay. In an electric field test, you have a chamber, you have 2 charged plates. You have plus charges on one plate, you have negative charges on another. Okay. And let's say you put a water molecule in there. Okay. Oh yeah, we've done partial negatives, partial positives before. One more time, water. Positive side, negative side because of electronegativity. That's ringing a bell. Tiny bit. So if you look at water, if we were to put it into an electric field, okay, we have a battery, positive, negative end, some sort of voltage source, and we connect it to two metal plates, okay? With strong enough voltage, this water molecule won't stay that way anymore, okay? If you just think about, well, shouldn't the negative side be pointing to the positive side of vice versa? You are absolutely correct, okay? Polar molecules will align. Even the word respond is good enough to an electric field. Okay, that's a experimental test you can do. Okay, yeah.
So how could you tell that the water is like lining up like that?
When things are aligned, they're going to have different optical properties. How light passes through it is going to be different versus if you have like if everything's aligned, the scattering may not be random. I think there might be also a way of measuring a potential difference in the conductivity as a result of how they align. To be honest, those are my guesses. I'm not entirely sure, but that's what, if I was told to do that, that's where I would go first. Okay. Great question. Okay. All right. Now let's get the shortcut. Okay. The purist in me has to give the technical definitions first. Okay. Now we're going to give our Chem 101 shortcut. Okay. If you go on to Chem 111 on forward, there's going to be 2 to 3% of molecules that won't work here. Okay. But there's an easy explanation of why. So if you're interested in that, I can explain it. But otherwise, this, I've never seen it not work in Chem 101. Okay. And so we're just going to say, polar molecule test. Okay. We're going to keep this a nice, easy flow chart with just 2 questions. That's it, just 2 questions. Okay. All right. First question we're going to ask is, are there, here's the key word, lone pairs on the central atom? I guess there's 2 key phrases. Okay. Are there lone pairs on the central atom?
Good.
And we got yes, or we got no. That's question number 1. And then question number 2. Do we have different outer atoms? Okay, the first question is a lone pair question. The second question is if you have difference in the outer atoms. And then again, we'll go yes or no. All right, and here's going to be your answers. If you got lone pairs in the central atom, if the answer is yes, you are a polar molecule. You have tripped the alarm. You're polar. Okay. What if you didn't have any lone pairs in the central atom, but you have different outer atom? Well, yeah, you're still going to have a difference in how charges separate out in your atom. You're going to lack symmetry. Okay. Polar molecules, said another way, don't have a good amount of symmetry to it. There's like a sidedness to it. Okay. Whereas if you're nonpolar, you're highly symmetrical. Okay. So you have to go no twice. That's harder to do. So you're going to see most molecules are going to be polar. Fewer forced to guess, okay, you'd have a higher chance of being correct.
What about a halogen?
Okay. A halogen would be okay, so for this, diatomics don't like perfectly fall into this, but if you have a diatomic, here we're gonna do the diatomics. This is like 3 or more atoms. If you have diatomics, okay, then instead of different outer atoms, you can just go different atoms. Okay. Yes, polar. No, non-polar. Yeah, so like you know, H2, N2, O2, F2, Cl2, Br2, I2, those 7, they're not different, but if you had like fluorine on a chlorine or HCl, you know, stuff like that, different polar. Okay. All right, and then let's do some examples of this. Okay. All right, so something with lone pairs on the central atom, water would easily be the best example of that. Water is your most stereotypical polar molecule. Ammonia. Okay. Like oxygen and nitrogen, they're electronegative elements and they have lone pairs on them. So you have like a negative side and then you have like a positive side, right? Or you can be more specific, putting the partial positives on like each of the hydrogen atoms. That works too. And what if like you don't have all the same outer atoms? Then it's going to be like even more polar. Okay. In the news lately is chloramine. Okay. I feel like water quality is often in the news. People are talking about fluoride. People are talking about chlorine in the drinking water. So chloramine is one of those chlorine sources in disaffecting the water. And this, the molecule that made the news, I forget how to pronounce it, but it's I forget, but it's like a byproduct of using this in treating drinking water. Okay, the catch-22 is you kill the microbes, but if you overdo this, you get too many byproducts. Those byproducts could be toxic, you know. I feel like chemistry is a whack-a-mole game. Like all the time you solve one problem, you create it. Okay. But this is chloramine. So like nitrogen and chlorine, they're both kind of electronegative. So this is kind of your negative side, and that's kind of your positive side. Right? Yeah. So polar molecules, they have sucky symmetry. They have like little to no symmetry. All right. Now, if you have a lone pair, it's easy to like bend your molecule and have a negative side and positive side. But what if you have no lone pairs? Okay. So a good example would be like cyanic acid. No lone pairs, but you can clearly see there's a negative side and then you have a positive side. Okay. Knowing those electronegative elements really help you. Okay. Nitrogen, oxygen, fluorine, I guess chlorine as well. Okay. Another one would be like, this one's a little weirder. Not too much weirder. Okay. Carbon, oxygen, sulfur. It's the cosine molecule, COS. All right. This is your more negative side. And sulfur has some electronegativity compared to carbon, but it's not as much. So you'd have like a really tiny negative there, and then your positives right here. So effectively, essentially speaking, this is your negative side and that's your positive side as an average. All right, so how about non-polar? Okay. You gotta have high symmetry. Okay. Carbon dioxide is my personal favorite. Okay. the negatives and positives are symmetrically distributed. You may say, well, wait. Oxygen's electronegative as all get out. Like you have a partial negative there and you have a partial negative there, and then you have a partial positive in the middle, double that of the oxygen. Yeah, you're right. You're right. But it's nonpolar because the negatives are perfectly averaged onto the center of carbon dioxide. Okay? I can show this in a picture. I'm going to try to prove this to you. You're going to be like, no, I can get it to stick. I can get it to stick. You can make a T-bone shape, Josh. You can get it to stick. Okay, I'm going to show you. And the real truth, the beyond Chem 101 truth is, yeah, maybe a tiny bit because things can like bend out of shape, but it's pretty darn minimal. Okay. It's mostly London dispersion force. So check this out. Okay. You're thinking, oh, you got to do a T-bone. Okay. Hopefully none of us get in that type of collision. Okay. Maybe you're thinking of this. It's like, I can do this, right? And I'll use charges, colors to really make points on. You got your partial negatives. Then you got your partial positives. You're like, surely this has to have an interaction, right? Okay. So again, the real truth, the 101, the beyond 101 truth is, yeah, tiny bit because these might be far away enough to help that a little bit, but it's made minimal and negligible because, well, they are there. Okay. And so what happens is basically this attraction, I don't know what color to use. This attraction here is negated by the repulsions here and here. Okay, so you have that attraction, but then you have repulsion here and there. Because there's no side to grab onto, there's no side to grab onto. Okay, that's why carbon dioxide, despite having like a decent mass to it, 44, it's not like heavy, but it's not like light either. It's a gas. It's a gas. Nothing to grab. Nothing to grab. Okay. Whereas water, you have a clear, so this is nonpolar. You have a clear positive side and negative side. Okay. And water is a perfect segue into the last intermolecular interaction of the day, which is hydrogen bonding. Okay, I need a new slide when you're ready. Friday, right? It's Friday. All right. Last slide, or last topic. Okay, we got hydrogen bonds. H bonds. Okay. Hydrogen bonds and uranium compounds, that was basically my PhD thesis. 80–90% of it. All right. In terms of academic content, reality, most of my thesis was fixing broken instruments all the time. All right. Anyways, so hydrogen bonds. Okay, this is a special category. Special, strong example of dipole-dipole. You still have permanent dipoles. Okay. But the hydrogen bond is marvelously strong. Some hydrogen bonds are so strong, they're almost as strong as covalent bonds. Okay. Right. Hydrogen bonds are hecka important. You take a biology class, they'll talk your head off about hydrogen bonds all day long. DNA base pairing, how cellulose, wood gets its strength from. There's just thousands of examples. I'm not even naming them all. Protein interactions. I mean, you name it. Okay. Now, protein, you have to have your substrate molecule, okay, fit perfectly into the enzyme pocket. Okay. It's like trying to land a lunar rover without crashing it, and you have to get a very specific position. Okay. All the hydrogen bondings will help that molecule land a place. Okay. But there'd be some hydrogen bonds that are tugged on just slightly elongate the bond, and that sets up that molecule for attack, and that's how an enzyme works. It sticks the landing for everywhere except one weak spot. You'll have a hydrogen bond getting slightly broken, and then you can break that bond, make a new bond. Okay, that's how enzymes work. So hydrogen bonds, what makes it so strong? Okay, first, let me show you the notation for a hydrogen bond. I'm exaggerating these dots to not confuse them with those dots. Okay. So what's an X? X is a nitrogen, an oxygen, or fluorine. So is Y. But the reason why I give them separate letters is they don't have to be the same element. Okay. And what we know about X or Y, the nitrogen, oxygen, or fluorines, is because they're electronegative, they're going to pull on electrons and they're going to carry a very decently strong partial negative charge. Okay. So we're going to have a partial negative on this Y, but check this out. Here's a lone pair. This is a lone pair. And lone pairs are like basically pure electrons. So we're going to have a very intense partial negative here as a result. Lone pair, singular. Okay. All right. Now, if X is also an electronegative element, it's sucking those electrons away from the hydrogen. Okay. That means I have a partial positive right here. Okay. And when it comes to hydrogen, hydrogen is small and has only one electron in its neutral state. So here's the magic of the hydrogen bond. Hydrogen only comes in with one electron. And this electronegative element is going to snatch its one and only electron pretty close to itself. Okay? Those electrons in a bond, instead of being centered in the middle, they're going to be kind of like right there, the electrons in a bond. Okay? So it's small, and it is it's small, and you only have one electron, it goes away, you're going to have a pretty darn intensely concentrated positive charge as a result. Small and highly charged. Okay, that is the magic of the hydrogen bond. Okay, small positive charge is going to be high. Okay, so this is powerfully concentrated. Okay. These hydrogen bonds, I mean, sometimes this X is sucking away almost half of the electron away. You're going to have almost half a positive charge in a hydrogen. Okay, that is. I wish I had more examples to give you context for it, but you'll just have to take my word for it. That is intensely strong. Okay, so this is almost like a cation-anion interaction. This is approaching ionic bonds sometimes. Okay. I mean, I'm selling it a little bit, but like, yeah, this is going to be way better than your standard dipole type. So like, let me show you dipole-dipole versus H bond. Okay. So in a dipole-dipole, you could have something like formaldehyde. You have a negative here, positive there. Negative there, positive there. And you'll have an interaction for sure. But you got bigger atoms. It's not as concentrated. You can have things in the way, you know, with an H bond, small hydrogen, electronegative elements. You have the best of the best, okay? Intense positive, intense negative, and so you get the best sticky. Right? So here's how you draw a hydrogen bond. I think I did already with water earlier, but let's just draw it again. So your notes are complete. Okay. This right here is your hydrogen bond. Negative, negative. Okay. And then here's some terminology. Okay. Whoever supplies a hydrogen, this is called your H bond donor. And wherever the hydrogen is pointing to, that's called your H bond acceptor. Okay. Donor, acceptor. So we can see with this water molecule, this is our donor. And this oxygen right here is our acceptor. And you can have a donor, you can have something be a donor in one spot, and it can also be an acceptor with respect to another spot. Let's see if I can draw that. Kind of out of room. But maybe I'll look at this one. Like here, this is a donor. We had another water right here, pointing its hydrogen towards it. That would now be an acceptor as well. Now it would become a donor. This is how you get your water H bonding networks like we have in our water boys. Donor, acceptor, but now it's going to be an acceptor as well. Donate to it. Okay. But again, the main point being hydrogen bonds are strongest because you have concentrated plus and concentrated minus. All righty. So I was trying to make myself go at a breakneck pace because I was scared of. I thought I was overtime. I have 4 minutes, so we can end a nice nifty example or two, and then we'll just call it a day. Oh, did I pull this too early? No. All right. Again, I'll leave my papers up if anyone wants to take them. All right, we'll do some examples. Okay. Let's draw a dipole-dipole between two SO2 molecules. It's a good one. And for the sake of time, in case it's been a while since you remembered sulfur dioxide, I'll just draw it for you. Okay. So you're gonna have to draw the second sulfur dioxide and get them to interact. Okay. All right, and then one more. Draw H bond between two HF molecules. Okay, the main thing with the dipole-dipole is if this was like an open-ended question, which I'm not going to have, but if it was an open-ended question, you just make sure your positive side is pointing to the negative side. Okay, if it looks a little different than your neighbors, I don't really care. There's probably more than one possible answer for this one because it's kind of it's got 3 atoms on it. We sit so much as a society. What was that new study out of Harvard? It's like even if you have moderate exercise in your life, if you still try to offset, you're sitting with moderate exercise, you're still, I don't know, more likely for X, Y, and Z. Well, I don't know. Yeah. As Bob Ross says, sometimes you just gotta stop reading the news, man. All right. All right, let's get out of here. So the second SO2, the way they classically teach this sort of molecule is to just have them literally in the same direction. I think in reality, this is not as realistic because if the negative charge is there, I think this would be like a little bit more offset and you'd have the sulfur pointing at it. I don't care if you had a little wiggle in the SO2 or not, just so long as if you have a negative or a positive point and a negative, that's happy. But I see this oftentimes in 101 textbooks, they just point the same direction, which is good enough, but it's a little bit cringe because it's not specific. But basically, if you're positive and negative are remotely within range of each other, I give it credit. Okay. And then for the HF, this one, there's really only one possibility, just point them right at each other. Good. Okay. There's your H bond. And we are perfectly at time. All right, so I'm gonna have a busy break. I'll try to enjoy it too. Look for some extra credit to be released as well as the study guide for exam 4. It'll be open. I'll probably have it open by Tuesday of next week. Yeah. I feel like I was supposed to say something else, but I don't remember. All right, that's what email's for.
Yep.
Hopefully people are still getting my normal emails, even though campus announcements have been wonky, so.
Still on computer or PowerSheet, that one, the four,
Oh, it's gonna it'll be a computer again.
on the computer, same.
Yeah, yeah. Same old deals. All righty, take care, have a great break.
You too.
You too.
Thank you, thank you, thank you.